Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. The Southern Song Dynasty, a period of artistic flourishing, also bore the weight of relentless external pressures. The Jurchen Jin dynasty controlled the north, casting a long shadow over the empire. Political instability simmered internally, marked by factionalism and court intrigues. This era, defined by both cultural brilliance and precarious existence, served as the backdrop for the life and work of Qin Jiushao. He emerged as a polymath, demonstrating capabilities that extended far beyond the confines of pure mathematics. His expertise encompassed astronomy, crucial for calendrical calculations, military strategy, an area of vital importance given the constant threat of invasion, and even music, a pursuit often linked to mathematical harmony in traditional Chinese thought. Qin Jiushao's mathematical endeavors were deeply intertwined with the practical concerns of his time. He did delve into abstractions, yet his work consistently sought to address tangible problems facing society. These ranged from land surveying and taxation to military logistics and astronomical observation. This pragmatic orientation distinguishes his contributions and highlights the integral role of mathematics in Song Dynasty China. His magnum opus, the Shushu Jiuzhang, or mathematical treatise in 9 sections, stands as a testament to his comprehensive understanding of mathematics and its applications. This work offers a structured exploration of contemporary mathematical challenges and the innovative solutions devised to overcome them. The treatise reflects the mathematical landscape of the Southern Song Dynasty, capturing both the inheritance of established traditions and the emergence of novel approaches. Qin Jiushao drew inspiration from earlier Chinese mathematical traditions, most notably the 9 chapters on the mathematical art, a foundational text that laid the groundwork for centuries of mathematical inquiry. The 9 chapters presented a collection of problems and methods, covering areas such as arithmetic, algebra, geometry, and surveying. Qin Jiushao expanded upon this foundation, refining existing techniques and introducing entirely new methodologies. He pushed the boundaries of mathematical knowledge, moving beyond established practices to address increasingly complex problems. One of Qin Jiushao's signal achievements lies in his formulation and application of the Chinese Remainder Theorem. This theorem, a cornerstone of number theory, provides a method for solving systems of simultaneous congruences. Its initial purpose, in Qin Jiushao's context, centered on resolving calendrical problems. These problems related to the determination of auspicious times and dates, a matter of considerable importance in a society deeply influenced by cosmological beliefs and ritual practices. Calendrical calculations in imperial China were far from simple exercises. They demanded a sophisticated understanding of astronomy, mathematics, and the intricate relationships between different cyclical systems. The Chinese calendar, a lunar-solar calendar, sought to harmonize the cycles of the sun and the moon, a task complicated by the fact that these cycles are not perfectly commensurable. Furthermore, the calendar incorporated various other cyclical systems, each with its own period and significance. The need to reconcile these different cycles presented a significant mathematical challenge. Determining when specific cycles would align or recur simultaneously required solving what are now recognized as systems of congruences. Qin Jiushao's Chinese Remainder Theorem provided a powerful tool for addressing these types of problems, enabling the accurate determination of dates and times that satisfied multiple calendrical conditions. This capability had profound implications for agricultural planning, religious observances, and the overall administration of the empire. The precise alignment of celestial events with earthly activities was believed to ensure harmony and prosperity, underscoring the practical and symbolic importance of Qin Jiushao's work. The broader context of Qin Jiushao's era includes the intellectual ferment of the Song Dynasty. This period witnessed a resurgence of Confucianism, known as Neo-Confucianism, which emphasized rigorous scholarship and moral self-cultivation. The rise of printing technology facilitated the widespread dissemination of knowledge, leading to increased literacy and intellectual engagement. While warfare and political instability posed constant challenges, the Southern Song Dynasty also fostered a vibrant intellectual climate that encouraged innovation and critical thinking. Qin Jiushao's contributions must be viewed within this dynamic context. He was a product of his time, shaped by the intellectual currents and practical demands of the Southern Song Dynasty. His deep understanding of mathematics, astronomy, and other disciplines allowed him to address pressing societal needs and make lasting contributions to the advancement of knowledge. His work exemplifies the intersection of theory and practice, demonstrating the power of mathematics to solve real-world problems and shape the course of human affairs. The shadow of the Jin dynasty loomed, yet within that shadow, intellectual light flourished, exemplified by figures such as Qin Jiushao. The Shushu Jiuzhang served not as a mere collection of mathematical techniques, but as a comprehensive guide to problem-solving in various domains. It showcased the versatility of mathematics and its applicability to a wide range of practical challenges. Qin Jiushao's treatise stands as a testament to his commitment to both theoretical rigor and practical relevance, reflecting the ethos of his era. He presented mathematics as a tool for understanding and shaping the world, a means of achieving both intellectual enlightenment and societal progress. The Chinese Remainder Theorem, as formulated by Qin Jiushao, offered a systematic approach to solving problems involving simultaneous congruences. While the concept of solving such problems had been explored in earlier mathematical traditions, Qin Jiushao's method provided a more general and efficient solution. It enabled mathematicians to tackle increasingly complex calendrical calculations and other problems that required the determination of a number satisfying multiple remainder conditions. This represented a significant advancement in number theory and its applications. The significance of determining auspicious times and dates in Qin Jiushao's era extended far beyond mere scheduling. It was deeply intertwined with the cosmological beliefs of the time, which held that the universe operated according to a set of mathematical principles. Aligning human activities with these principles was believed to ensure harmony and prosperity, while deviations could lead to misfortune and disaster. Calendrical calculations, therefore, were not simply technical exercises, but rather acts of cosmic significance. Qin Jiushao's work contributed to this larger project of aligning human society with the rhythms of the universe, underscoring the profound cultural and spiritual dimensions of his mathematical endeavors. The problems addressed in Shushu Jiuzhang ranged from determining land areas to calculating tax burdens, from designing fortifications to predicting celestial events. Each problem presented a unique challenge, requiring the application of mathematical principles and techniques. Qin Jiushao's solutions demonstrated his mastery of these principles and his ability to adapt them to diverse contexts. His treatise served as a valuable resource for officials, engineers, and scholars alike, providing them with the tools they needed to solve practical problems and advance their understanding of the world. The legacy of Qin Jiushao extends far beyond his specific mathematical contributions. He exemplified the spirit of innovation and inquiry that characterized the Song dynasty. His commitment to both theoretical rigor and practical relevance continues to inspire mathematicians and scientists today. His Shushu Jiuzhang stands as a testament to the power of mathematics to solve real-world problems and shape the course of human civilization. His work remains a valuable resource for understanding the history of mathematics in China and the enduring contributions of Chinese mathematicians to the global body of knowledge. Qin Jiushao's brilliance shone particularly brightly in his treatment of indeterminate analysis, specifically his masterful application of what is now known as the Chinese Remainder Theorem. This theorem, while having roots in earlier mathematical traditions, received its most complete and sophisticated exposition in Qin's Shushu Jiuzhang. The impetus for this development stemmed from a very practical concern: the construction and maintenance of accurate calendars, a matter of utmost importance in dynastic China. The Southern Song Dynasty faced significant calendrical challenges. Accurate calendars were essential for agriculture, governance, and religious observances. Discrepancies in the calendar could lead to disruptions in planting cycles, miscalculations of auspicious dates, and a general erosion of public trust in the ruling authority. The calendar was more than a practical tool. It was a symbol of cosmic order and the emperor's mandate to rule. One of the central problems in calendar construction was the synchronization of different cyclical systems. The Chinese calendar traditionally incorporated multiple cycles of varying lengths, days, months, years, and larger cycles based on astronomical observations. Each of these cycles had its own period, and aligning them required finding a common point of reference. This task presented a formidable mathematical challenge, particularly when dealing with cycles that were incommensurable, meaning their lengths did not have a simple common divisor. The Chinese Remainder Theorem provided a powerful tool for solving this synchronization problem. It addresses the question: given a set of congruences, can we find a number that satisfies all of them simultaneously? In other words, if we know the remainders when a number is divided by several different divisors, can we determine the number itself? This is precisely the type of problem encountered when trying to align different cyclical systems in the calendar. Imagine, for instance, attempting to synchronize 3 cycles, one of length 3, one of length 5, and one of length 7. Suppose we know that at a particular point in time, the first cycle is at position 1, the second cycle is at position 2, and the third cycle is at position 3. The Chinese Remainder Theorem allows us to find the smallest number that satisfies these conditions, that is, a number which, when divided by 3, leaves a remainder of 1. When divided by 5, leaves a remainder of 2, and when divided by 7, leaves a remainder of 3. Qin Jiushao's contribution was to provide a general algorithm for solving such systems of congruences. His method, described in detail in the Shushu Jiuzhang, involved a series of modular multiplications and additions. It is an iterative process that systematically reduces the problem to a single congruence, which can then be solved directly. To illustrate Qin's method, consider a simplified example drawn from the spirit of problems found in Shushu Jiuzhang, although adapted for clarity. Suppose we seek a number, let us call it x, that satisfies the following conditions: leaves a remainder of 2 when divided by 3. X leaves a remainder of 3 when divided by 5. In modern notation, this can be written as x is congruent to 2, modulo 3. X is congruent to 3, modulo 5. Qin's method involves finding what he called the multiplication constant for each modulus. For the modulus 3, we seek a number that, when multiplied by 3, leaves a remainder of 1 when divided by 5. The other modulus, this number is 2, since 3 times 2 equals 6, which leaves a remainder of 1 when divided by 5. Similarly, for the modulus 5, we seek a number that, when multiplied by 5, leaves a remainder of 1 when divided by 3. This number is 2, since 5 times 2 equals 10, which leaves a remainder of 1 when divided by 3. Next, we multiply each remainder as by its corresponding modulus and multiplication constant.
2 remainder times 5, modulus times 2, multiplication constant equals 20. 3 remainder times 3, modulus times 2, multiplication constant equals 18. Finally, we add these products together. 20 plus 18 equals 38. This sum, 38, is a solution to the system of congruences. However, it is often desirable to find the smallest positive solution. To do this, we find the least common multiple of the moduli, which in this case is 3 times 5 or 15. We then subtract multiples of 15 from 38 until we obtain a number between 0 and 15. 38 minus 2 times 15 equals 8. Therefore, 8 is the smallest positive solution to the system of congruences. Indeed, 8 leaves a remainder of 2 when divided by 3, and it leaves a remainder of 3 when divided by 5. Qin's actual algorithm, as presented in the Shushu Jiuzhang, is considerably more complex than this simplified example, involving intricate calculations with Abasi and specialized terminology. However, the underlying principle remains the same: to systematically combine the information from the individual congruences to arrive at a solution that satisfies all of them simultaneously. A key advantage of Qin's method is its computational efficiency, particularly when dealing with large numbers. The iterative nature of the algorithm allows for the problem to be broken down into smaller, more manageable steps. This was crucial in a time before modern computers, when calculations had to be performed by hand, or rather by abacus. Furthermore, while Qin Jiushao primarily dealt with cases where the moduli were co-prime, meaning they shared no common factors, his method could be adapted to handle non-co-prime moduli as well, albeit with some modifications. This is a significant point, as many real-world problems, including those encountered in calendar construction, involve non-co-prime numbers. The Chinese Remainder Theorem, as formulated and applied by Qin Jiushao, provided a powerful tool for solving a wide range of problems beyond calendar construction. It found applications in areas such as surveying, civil engineering, and even military logistics. The ability to determine a number that satisfies multiple remainder conditions is a fundamental mathematical technique with far-reaching consequences. His contribution to this area solidified his place as one of the most important mathematicians of the Song Dynasty, and his insights continue to resonate within the broader history of mathematics. The ability to determine a number that satisfies multiple remainder conditions is a fundamental mathematical technique with far-reaching consequences. His contribution to this area solidified his place as one of the most important mathematicians of the Song Dynasty, and his insights continue to resonate within the broader history of mathematics. Beyond his profound contributions to indeterminate analysis, Qin Jiushao also made significant strides in the realm of polynomial equations. He devised a method for solving high-degree polynomial equations numerically, a technique that bears a striking resemblance to what is known in the West as Horner's method. Qin's work in this area is particularly noteworthy, given that he developed it independently nearly 5 centuries before William George Horner formally presented his method in 1819. The need to solve polynomial equations, particularly those of higher degrees, stemmed from various practical problems prevalent during Qin's time. Determining areas and volumes of complex shapes, for example, often led to equations that were beyond the scope of simple algebra. Land surveying, irrigation projects, and other engineering endeavors frequently required finding precise numerical solutions to polynomial equations to ensure accuracy and efficiency. The challenge lay in finding a systematic and reliable approach to tackle these equations, especially when exact solutions were unattainable through traditional algebraic manipulations. Qin Jiushao's method provided an innovative solution to this challenge. It was an iterative process, allowing for the approximation of roots with increasing accuracy. This numerical approach was particularly valuable in a context where symbolic algebra was comparatively less developed than its later European counterpart. The method involved a series of successive approximations, refining the estimate of the root at each step until a satisfactory level of precision was achieved. It was a testament to Qin's deep understanding of numerical analysis and his ability to devise practical algorithms for solving complex mathematical problems. To appreciate the novelty of Qin's approach, it is essential to consider the state of Chinese mathematics at the time. While Chinese mathematicians had a long and rich tradition of solving linear and quadratic equations, methods for tackling higher-degree polynomials were less established. Qin's method represented a significant leap forward, offering a general technique applicable to polynomials of any degree. This was a departure from earlier approaches that often relied on specific tricks or ad hoc solutions tailored to particular types of equations. Qin's method, in contrast, provided a unified framework for approximating the roots of a wide range of polynomial equations, regardless of their specific form. Qin's method for solving polynomial equations, as detailed in his Shushu Jiuzhang, involves a systematic process of successive approximation. He begins with an initial estimate of the root and then refines this estimate through a series of iterative steps. Each step involves evaluating the polynomial at the current estimate and using this value to adjust the estimate in a way that brings it closer to the true root. This process is repeated until the desired level of accuracy is achieved. The core idea behind Qin's method is to exploit the relationship between the polynomial and its derivative. By evaluating the polynomial and its derivative at the current estimate, one can obtain information about the slope of the polynomial at that point. This information can then be used to determine how to adjust the estimate to move closer to the root. The method is essentially a discrete approximation of Newton's method, a powerful technique for finding roots of differentiable functions. A key aspect of Qin's method is its reliance on the concept of positive-negative signs OK-far, which translates to something along the lines of alternating positive and negative coefficients in root extraction. This concept is intricately linked to the process of finding the numerical roots of polynomial equations, and it reflects the ingenuity of Chinese mathematical thought during that era. The method involves strategically manipulating the coefficients of the polynomial equation to facilitate the extraction of its roots. This manipulation often involves alternating the signs of the coefficients in a specific manner, which allows for a more efficient and accurate approximation of the roots. This technique showcases the deep understanding of polynomial equations and their properties that Qin Jiushao possessed. The iterative nature of Qin's method is well suited to the computational tools available at the time, namely the counting rods. While cumbersome by modern standards, the abacus provided a reliable means of performing the arithmetic operations required by the method. Qin's method cleverly minimizes the number of operations required at each step, making it computationally feasible even for high-degree polynomials. This is a testament to Qin's skill in designing algorithms that were both mathematically sound and practically implementable. When comparing Qin's method with the later Horner's method, several similarities and differences emerge. Both methods are iterative techniques for approximating the roots of polynomial equations. Both rely on successive refinement of an initial estimate, and both exploit the relationship between the polynomial and its derivative. The core mathematical principles underlying the two methods are essentially the same. However, there are also notable differences in notation and implementation. Qin's method, as presented in Shushu Jiuzhang, is described in a more algorithmic and procedural style, reflecting the practical focus of Chinese mathematics at the time. Horner's method, on the other hand, is often presented in a more algebraic and symbolic form, reflecting the later development of symbolic algebra in the West. Chun's method also relies heavily on the use of counting rods, while Horner's method is typically implemented using more modern computational tools. Furthermore, the historical context in which the two methods were developed is quite different. Qin Jiushao worked in a relatively isolated mathematical tradition with limited interaction with other cultures. William George Horner, on the other hand, was part of a broader European mathematical community with access to a wider range of ideas and techniques. This difference in context likely influenced the way in which the two methods were formulated and presented. Despite these differences, the fundamental similarity between Qin's method and Horner's method is undeniable. Both represent significant advances in the field of numerical analysis, and both provide effective techniques for solving polynomial equations. Qin's independent discovery of this method, centuries before its rediscovery in the West, is a testament to his mathematical genius and the ingenuity of Chinese mathematical thought. His work serves as a reminder that mathematical innovation can arise in diverse cultural contexts, and that different traditions can often converge on similar ideas independently. The impact of Shushu Jiuzhang resonated through subsequent generations of Chinese mathematicians, shaping the landscape of algebraic thought within the empire. Its influence is discernible in later mathematical texts, where Qin's methods were refined, adapted, and applied to an ever-widening array of practical problems. The systematic approach he championed, combining theoretical insights with concrete applications, became a hallmark of Chinese mathematics. The reception of Qin Jiushang's work, however, presents a complex historical picture. While Shushu Jiuzhang was undoubtedly influential, its impact was perhaps more deeply felt within specific circles of scholars and practitioners than across the entirety of Chinese society. The transmission of mathematical knowledge in that era was often dependent on personal mentorship and the availability of printed materials, factors that could limit the dissemination of even the most groundbreaking ideas. The book was included in the Yongle Encyclopedia, a Ming Dynasty project of immense scope, a testament to its perceived value. Assessing Qin Jishao's broader influence presents unique challenges, largely due to the relative isolation of Chinese mathematics from its Western counterpart during that period. Lines of direct influence and intellectual exchange are difficult to trace, making it challenging to compare his achievements directly with those of his contemporaries in other parts of the world. The evolution of mathematical ideas within China followed its own distinct trajectory, shaped by its unique cultural and intellectual context. Despite these challenges, the significance of Qin Jishao's contributions remains undeniable. His work provides a valuable window into the state of mathematical knowledge in China during the Southern Song Dynasty, revealing a sophisticated understanding of algebra, numerical methods, and their applications to real-world problems. His solutions to polynomial equations, indeterminate analysis, and surveying problems demonstrate a remarkable level of ingenuity and mathematical skill. Qin Jiushao occupies a unique position in the history of mathematics, a mathematician deeply embedded in a turbulent historical context. His life and work were shaped by the political instability and social upheaval of the Southern Song Dynasty, a period marked by war, invasion, and profound cultural change. Despite these challenges, he managed to produce a work of lasting mathematical significance, demonstrating the resilience and adaptability of the human intellect in the face of adversity. The enduring value of Qin Jishao's work lies in its practical approach to mathematics. He was primarily concerned with developing methods for solving concrete problems, whether it was calculating land areas, determining tax rates, or constructing irrigation systems. This focus on practical applications made his work highly relevant to the needs of his society, and it contributed to the development of a uniquely Chinese tradition of applied mathematics. His ability to develop innovative solutions to real-world problems is a testament to his mathematical genius. The methods he devised for solving polynomial equations, indeterminate equations, and systems of linear congruences are all remarkable achievements, demonstrating a deep understanding of mathematical principles and a keen ability to apply them to complex practical situations. The story of Qin Jiushao and his work offers insights into the relationship between mathematics, society, and culture in the Southern Song Dynasty. His contributions reflect the practical concerns of his time, the intellectual traditions of Chinese mathematics, and the social and political context in which he lived. His work provides a glimpse into a world where mathematical knowledge was valued for its practical utility and its ability to contribute to the well-being of society. Qin Jiushao's Shushu Jiuzhang stands as a testament to the ingenuity and resilience of Chinese mathematical thought during a period of significant social and political upheaval. It is a reminder that mathematical innovation can arise in diverse cultural contexts, and that different traditions can often converge on similar ideas independently. The legacy of Qin Jiushao extends beyond the specific mathematical techniques he developed. His work serves as an inspiration to mathematicians and scholars around the world, demonstrating the power of human intellect to overcome challenges and to create knowledge that can benefit society. His contributions enrich our understanding of the global history of mathematics, revealing the diverse and multifaceted ways in which mathematical ideas have been developed and applied across different cultures and time periods. His story underscores the importance of preserving and studying the mathematical traditions of different cultures. By examining the work of mathematicians like Qin Jiushao, we can gain a deeper appreciation for the richness and diversity of human mathematical thought. We can also learn valuable lessons about the relationship between mathematics, society, and culture, and about the ways in which mathematical knowledge can be used to address real-world problems. Qin Jiushao's work reminds us that mathematics is not simply an abstract intellectual pursuit, but a powerful tool that can be used to improve the lives of people around the world. His legacy is a call to continue exploring the frontiers of mathematical knowledge and to apply that knowledge to the challenges facing our society today. The mathematical landscape is vast, and its exploration continues, enriched by the contributions of those who came before us. His contributions serve as a reminder of the power of human ingenuity and the enduring value of mathematical thought.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.